Welcome to Derektronic, where we experiment, learn, and build with electronics. As a follow-up to my most recent video, let us now construct a monostable multivibrator circuit. But before we do that, let us first compare the stable multivibrator, the one we did in the previous video, with the monostable multivibrator, the one we will be doing today. Now, let's start with the stable multivibrator. In terms of its characteristic, they are as follows. It's called a free-running multivibrator. It has no stable states. And as you saw in the previous video, the output continuously switches between two states, the on and off state, without the use of an external trigger. The waveform looks something like this. If you could remember from the previous video, the LED connected to the output was switching on and off, on and off, on and off by itself, without any external trigger being pressed on the circuit itself. It's just turning on and off by itself. That's why the stable multivibrator is known as a free-running multivibrator because there are no external triggers, and it has also no stable states. Now, for the monostable multivibrator circuit, these are its key characteristics. It's known as a one-shot multivibrator. We'll explain that later. It has one stable state, and this one is important, okay? Here's the waveform explaining that. A monostable multivibrator produces a single output pulse when triggered by an input signal. So what will happen in our video today, we will be connecting a sort of a triggering mechanism to our trigger pin. That will be pin number 2 of our multivibrator. We will be connecting a trigger mechanism there, okay, wherein if I press that mechanism, the output of the monostable multivibrator, the one on pin 3, okay, will go from its stable state, which is most probably the LED is off, to on, the unstable state. Now, while here at the unstable state, okay, there will come a time when the LED will turn off by itself. So when I trigger, that would be most probably a push button switch. We're going to connect on the trigger pin of our monostable multivibrator. When I trigger now, when I press the push button switch, the LED would be on for a limited time. Then it will switch off again. So if I want the LED on again, I need to push again the trigger so that it goes on again for a limited time again, and it's going to go off. This is the reason why a monostable multivibrator circuit or a monostable multivibrator is known as a one-shot multivibrator. The one stable state of the monostable multivibrator is the low state of the LED. The unstable state is the high state or the on state of the LED. Now, the circuit of our monostable multivibrator using a 555 timer would look like this. So as you can see, just like in our previous video, we will also be using the 555 timer integrated circuit to construct our monostable multivibrator. Let us interface the pin numbers of the 555 timer so that would be easier to explain there. Now, just like in the previous video, like in the stable multivibrator, pin 1, the ground pin, and pin 8, the VCC pin of our 555 timer will be connected to ground and the positive terminal of the 5 volts, as you can see here, respectively. The output pin of our 555 timer, that will be pin number 3, will be connected to a 330 ohm resistor this time around, 330 ohm, and that 330 ohm resistor will be connected to the anode of a blue LED, with the cathode of the blue LED connected to ground. Now, on the left-hand side, okay, let's take a look at first the triggering mechanism that I mentioned earlier, the one connected on pin number 2, trigger pin. Okay, now, the triggering mechanism of our 555 time or monostable multivibrator circuit would look like this, okay? We have a 1.5 kilo ohm connected to VCC, to the 5 volt source, okay, in series with a push button switch here, as you can see here at the bottom. Now, our trigger pin will be connected between the 1.5 kilo ohm resistor and the triggering switch here, our push button switch here. Okay, this pin number 2. Now, the other components connected to our 555 timer as follows. Okay, we have a 10 kilo ohm resistor, as you can see here, connected in series with a 47 microfarad capacitor, as you can see here, or C1. Now, R1 is connected to VCC. C1, 47 microfarad capacitor, is connected to ground. Now, in the junction between them, we will connect pin 6, that would be the threshold pin of our 555 timer, and pin 7, the discharge pin of our 555 timer, connected in the junction between the 10 kilo ohm resistor and the 47 microfarad capacitor, as you can see here. Now, on pin 5, we have a capacitor connected to it, connected to ground. Okay, C2, we're gonna connect a 10 nanofarad capacitor with the negative terminal of that capacitor connected to ground. Now, in the previous video, we left pin 5 unconnected. Why is that so? Okay, the function of this second capacitor, the 10 nanofarad capacitor you see here, is to filter any noise coming from a triggering mechanism. This will actually stabilize the operation of our 555 timer. Now, since in the stable multivibrator, we don't have anything triggering it because it's a free-running multivibrator, we don't have any need for a capacitor like this one in the stable multivibrator. However, here, in the monostable multivibrator, we have a triggering mechanism here, this push-button switch. So, this capacitor now will serve the purpose of filtering any noise or any unwanted signal coming from the input, making the operation of our 555 timer or our monostable multivibrator circuit much more stable. Alright, by the way, we also have the connection of the oscilloscope here. As you can see here, the positive or channel A of the oscilloscope, the positive terminal, that will be Y1 in our Country Lab Protoboard, will be connected to the output, similar to our previous video. And channel B, the positive of channel B, this will be Y2, the Y2 pin of our Country Lab Protoboard will be connected to C1 here, to the C1 capacitor. So what you will see on channel B is the capacitor voltage waveform, C1 in particular waveform. Now let us see the operation of a monostable multivibrator. We have the diagram here at the middle illustrating that. Okay. Now, as I've explained earlier, the monostable multivibrator circuit has a trigger pulse here, or a triggering mechanism here. That would be our push button switch. This is a negative trigger pulse. So what is meant by that? Okay, initially, okay, when the push button, we're gonna use a push button switch here. When the push button switch is not pressed, the signal here on pin number 2 is high because it's connected actually to the positive terminal of our power supply, our DC supply source, through the R2 resistor. Now, okay, now once I press the push button switch, now the trigger here, the trigger pin, will now get a low signal from this junction, because once I press this one, okay, this push button switch will force the input here on the trigger pin to go low, because this one is connected to the push button switch is connected directly to ground. So that's the purpose. So we have a negative trigger pulse here. Now, as explained earlier, once I press the push button switch here, okay, the output, okay, the output will go from its stable state, which is the LED being off, to its unstable state, the LED being on. And the LED will be on for a particular period of time. What would dictate how much time would that be? Okay, the length of time of the unstable state for the monostable output will be dependent on the capacitor voltage C1 and the resistor value here, R1, not capacitor voltage, the value of C1 and the value of the resistor here. computed using this formula. T, the period of that on state of our monostable multivibrator. T will be equal to 1.1 multiplied by the value of R1 multiplied by the value of C1. Now, if I would have a particular channel, one channel of my oscilloscope connected here, at the capacitor voltage here in this junction, what will I see on that particular channel? You will see the capacitor voltage waveform, see here here on the right hand side of the diagram. Now, to illustrate how that operates, okay? Once I press on, once I push the push button switch, once I press the push button switch, the capacitor will start charging. Here, capacitor C1 in particular will start charging. Now, once the capacitor voltage reaches around 2/3 of the VCC, the supply voltage here, the capacitor will start to discharge immediately. Now, during that charging state, the LED is on its on state, or the LED is on. Now, once the capacitor reaches 2/3 of the VCC, it will start to discharge immediately, which will put the LED on its off state. So the LED will be on during the charging of the capacitor, and it will be off once the capacitor reaches or start discharging right away. Let us now construct our monostable multivibrator circuit. And just like in my most recent video, I'm going to use this COM3 Lab Protoboard. What you see on the breadboard right now of the Protoboard is our 555 timer. I have it here. It's a 555 timer. And here, I have my tactile switch, or my push button switch here at the bottom here. Now, just like what I did with the stable multivibrator circuit, what I'm going to do first is this, okay? Let me first establish the positive 5-volt power rail and the negative and the ground power rail in our circuit. And just like in the previous video, we utilized also the 5-volt supply here, fixed supply. So I have the 5-volt here and the ground here. So what I'll do, same like before, I'll connect a red wire on the 5-volt source and the 5-volt pin here, and use the top power rail, the red one, the top red power rail for my 5 volts there. Okay, and the bottom, okay, blue power rail will be the ground. So I'll connect one to ground, and I'm going to use the bottom blue power rail for the ground. Bottom blue. There. So now establish top power rail red, 5 volts, and the bottom power rail blue would be the ground. Now, let us now connect the wires and components needed by our multivibrator as monostable multivibrator circuit. To start off, let's connect the ground pin, pin number 1, and the VCC pin number 8 of our 555 timer first. Okay, so ground, okay, pin 1, ground, will have to be grounded. So let's do that now. So it's connected here at the bottom, as you can see there, where the ground wire is connected. Okay, and the positive VCC pin 8 will have to be connected to the top power rail there, red top power rail, VCC at the top, as you can see there. Okay, now after that, let's establish the output again. Okay, now for the output, okay, which is pin number 3 of our 555 timer. I need to connect this time around a 330 ohm resistor. I have it here, 330 ohm resistor. One leg to pin 3, the other leg to a free pin. Okay, let's do that now. Okay, one leg to pin number 3, the other leg to a free pin. Somewhere on the right hand side of the 555 timer. There. Over there. Okay, this leg is connected to pin 3. Now, the other leg of the resistor, this leg, will have to be connected to, okay, this time around we are using a blue LED, this one. Where will that leg be connected? The leg of the 330 ohm resistor connected, it has to be connected to the anode terminal, the longer leg of our blue LED. Okay, let's do that now, okay? Longer leg, blue LED, anode, connected to 330 ohm resistor. The other leg, which is the cathode, is connected here on a free pin, okay? That cathode would need to be grounded according to the schematic diagram. Let's do that now. I'll ground now the cathode. You see there. Cathode grounded. Now, let's do this now, okay? So that's our output. Now, in this particular circuit, the monostable multivibrator circuit, we are using now pin number 5, the control pin. And based on the schematic, pin number 5, okay, we're using a 10 nanofarad capacitor. I have it here. Now, which terminal of the 10 nanofarad capacitor will be connected to pin number 5? We have to connect the positive terminal. That will be the longer leg, okay, of this capacitor. Now, the negative leg of the capacitor will have to be connected to ground. Let's do that now. So, 10 nanofarad capacitor connected to pin 5. Longer leg, pin 5. Shorter leg on the free pin. And that leg, let me use a longer jumper wire. That leg of that capacitor will have to be connected to ground. See here. Ground connection. Pin 5. Now, pin number 4, just like in the stable multivibrator circuit, will have to be connected to positive 5 volts. Let's do that now. Pin number 4, connected to positive 5 volts. There. Pin number 4, positive 5 volts. Okay. Now, the other components, let's connect it now. Okay. Starting off with our 10 kilo ohm resistor. See here. Okay. Now, our 10 kilo ohm resistor, okay, will have to be connected to 5 volts based on the schematic. Let's do that now. Okay. So 10 kilo ohm resistor, I'll connect it to a 5 volt line, the one at the top. Let's do that here. That. There. 10 kilo ohm connected to 5 volts and the other leg to a free pin. Now, that other leg of that resistor, the 10 kilo ohm resistor in particular, okay, will have to be connected to a capacitor. Based on the schematic, we're using a 47 microfarad capacitor for this purpose. Now, which leg of the capacitor, because there are 2 terminals of this capacitor to be connected to the 10 kilo ohm resistor, I need to connect the longer leg, which is the positive leg of the capacitor. The negative leg of the capacitor will have to be grounded. Let's do that now. Okay, so capacitor connected to the resistor here, longer leg. There. The shorter leg connected on the other side. See here. And this leg, the negative terminal of that capacitor, the 47 microfarad capacitor, will have to be connected to ground. Let's do that now. So capacitor, negative, connected to ground. See here. Okay. Now, let's take a look at now this tactile switch here, the push button switch. Now, just a quick course on tactile switches. Okay, tactile switches like this one, push button switches, have 4 terminals. Okay, 1, 2, 3, 4. That's 4 pins. Now, you have to connect your wires on 2 pins that are not connected. And which are they? Okay, either the corner, so either this one, top left and bottom right here, or the top right and the bottom left here. So it could be at the corner or the 2 pins on the same side. This one and this one can be used. Also on the other side. This one can also be used. Okay? Now, these 2 pins, the one on the left, and the one on the right, these 2 pins on the right, and the ones on the left, 2 pins on the left. Okay? Don't ever use these 2 pins for your wires. Why? Because these 2 pins, the one on the right and the one on the left, are actually connected. So you will be shorting the tactile switch or the push button switch if you do something like that. So what I'll do is this, okay? According to the circuit, okay, I'm going to use a 1.5 kilo ohm resistor. I have it here. I'll connect it to one terminal of our push button switch. Okay, let me do that. Okay, let me use the top leg there. Okay, top leg here, top right. Okay, I'm going to connect my 1.5 kilo ohm here. Okay, connect it somewhere here like that. Like there. Okay, so my 1 kilo ohm resistor here is connected to this upper left-hand leg of that tactile switch here. Now, the other leg, according to the schematic, will have to be connected to 5 volts. Let's do that now. 5 volts. There. 5 volts. Connected to 5 volts. Now, to establish a connection to ground, because we need to ground also this tactile switch, okay? So I have a choice. I could either use the top right pin or the bottom right pin to connect to ground, because these two pins are not connected to the upper left-hand pin here. I cannot use this pin, the lower left-hand pin, because this pin is connected to that, will be connected to that leg of that resistor. I'm going to short the push button switch if I do that. Okay, so let me use this bottom pin. Okay, so from the bottom pin here, okay, according to the schematic, this has to be grounded. So I'll ground it, as you can see right there. Okay, now the connection between this section of that circuit, okay, to the NE555 is through the trigger pin, because this is our triggering mechanism for our monostable multivibrator, okay? The push button switch here and this 1.5 kilo ohm resistor. So I need to connect this junction between the 1.5 kilo ohm resistor and the push button switch to pin number 2 of our monostable multivibrator circuit. So let me just do that. Pin number 2 of the 555 timer will have to be connected in this junction, okay? Let me do that now. Pin number 2. Okay. Pin 2 here. There. Let me do that. Let me just fix the wireless, okay? There you go. Pin number 2. There. Pin 2. Connected to the junction between the 1.5 kilo ohm resistor and the push button switch. There. Okay, let's complete the connections now, okay? According to the schematic diagram, pin 6 here, pin 6 is connected to the junction between the capacitor, the 47 microfarad capacitor, and the 10 kilo ohm resistor. Let's do that now, okay? Pin 6 is connected there. There. It's pin 6. Okay. Also, pin 7, the discharge pin. Also, discharge pin is pin 7. Pin 7, okay, is connected also to the same junction between the capacitor and the 10 kilo ohm resistor. Okay, so let me just do that again. There. So with that, our circuit is more or less complete. See there. Now, what I'll do right now, I'm going to switch on the board and try to observe the blue LED once I press the push button switch. I have now switched on our COM3 Lab Protoboard through the switch here, the upper right hand side, and also here on the power supply, on the fixed power supply section, there's a switch here. Okay, now let us now observe the blue LED. Okay, now this is a monostable multivibrator circuit, which means right now the blue LED is off, is in its stable state. However, when I press the push button switch here, the circuit will go to its unstable state. In the unstable state, that LED will be on, and it will be on for a certain period of time. Let's see if that happens. Okay, let me press the push button switch here. See there. So you can see there that the blue LED turn on for maybe a little over 1 second. There. Then it went off again. So at the on state, when the LED is on, that's the unstable state of our multivibrator. Then when it is off state, that's the stable state of our monostable multivibrator. You can see here. So I could put it on, and it will switch off automatically. Now, based on our theoretical discussion earlier, how long will that on state or that unstable state be? The period. What's the period of that on state? Now, the period of that on state or the unstable state of the LED, where the LED will be on for a while, okay, will be dependent on the value of this capacitor, 47 microfarad capacitor, and that resistor. Based on the formula, we could actually compute for that. Okay, now, the discharging time, the charging and discharging time of that capacitor will determine exactly how long that on state is, okay? Which means, okay, if I change the capacitor to a different value, let's say from 47 microfarad, I put it on a lower value, let's say 10 microfarad. We expect the on state to be shorter. Now, if I change the capacitor to a higher value, let's say 100 microfarad or 220 microfarad, for instance, we expect the on state or the unstable state of our multivibrator circuit to be longer. Let's do that now. I have two more capacitors here. The one on the left is a 100 microfarad capacitor. The one on the right is a 220 microfarad capacitor. Let's observe the on state or the unstable state of the blue LED once I have this on the board. Let's now replace first the 47 microfarad. I'll start with this one, 10 microfarad first. Let me insert this one here. There. 10 microfarad inserted. Let me just not try to squish the capacitor too much. Okay, here. There. Yeah, okay. Now, see now, okay? I'll switch. Insert the blue LED now, okay? So it's higher value than the 47. See, the on state or the blue LED is on for a longer period compared to what we have earlier. See, it's almost 2 seconds actually. Okay, so if I again change the 100 microfarad capacitor, this one, with the even higher value capacitor, like what I have here, I have a 220 microfarad capacitor here. We can expect now the blue LED to turn on longer before it switches off automatically. Let's do that now. Okay, there. So I have a 220 microfarad capacitor here right now. So let's see. Blue LED here. Let's observe the blue LED that we have here, okay? See, it's longer. See? That's more than almost 3 seconds. It's on. See? So based on the theoretical discussion, it is actually the charging and discharging of the capacitor that will determine that on state. However, that resistor, the value of that resistor at the top, that the 10 kilo ohm resistor will also have a say on that on state, that unstable state. Okay, we will see that once we go into the COM3 Lab companion software section when we display the waveforms. So here, let me return the original 47 microfarad capacitor. So there, little over a second, it's on. Okay, now, to see that waveform discussed in the theoretical discussion, I need to connect the oscilloscope here at the top. Okay, just like in the previous video, the oscilloscope connection will be something like this, okay? Y1 will be connected to the output. Output of our 555 timer is pin number 3. So I need to connect it to pin number 3. Let's do that now, huh? Pin number 3. So I have to be very careful here so that not to bend any of the other legs. There. Okay? Pin number 3. Closer here. There. Pin number 3. Where this resistor is also connected. The 330 ohm resistor is connected. It's pin number 3. So Y1 on pin number 3. Okay. Now Y2. Let's connect one red wire on Y2. Will be connected to the junction between the capacitor and the resistor, the 10 kilo ohm resistor. Let's have a closer look at that one, okay? This junction here. Now, let me remove the two wires coming from pin 6 and pin 7 first. Let me connect the oscilloscope Y2 line first. Okay, there. Okay, then I'll reconnect again these two. There. There. Junction between the capacitor and the 10 kilo ohm resistor. I have it there. Okay. And last, our COM connection
common connection for our oscilloscope, will have to be connected to ground, okay, the ground terminal here. So that will be the blue line, blue power rail down here, way down. So I connect the blue power rail. Now, once that is done, okay, we can now proceed to the Country Lab companion software to observe the waveforms. Now that we have wired the oscilloscope to our monostable multivibrator circuit, let us now observe the capacitor voltage and output waveforms of this same circuit using this Country Lab companion software. Let's open now the oscilloscope first. Okay, let me put the display here on the right hand side, make it a little bit bigger. There, okay, I'll check on Y2, click preview, and I'll run it. There. Now, when you see something like that for our monostable multivibrator circuit, don't panic, okay? Because right now, our monostable multivibrator is in its stable state. Okay, it's 0. The LED is off. I have to push I have to press the push button switch so that it will go to its unstable state. Now, once there, you're going to see a waveform once I do that. Let's do that now. I'll press the push button switch. Oops. I think the setting is too wide. The waveforms are too wide. Let me change the horizontal time division setting first. Let's put it at 200 milliseconds, something higher, okay, so that the waveform will be a little bit narrower. See? I'm getting waveform. Yeah, I'm getting one, okay? So what I'll do is this, by the way, okay? Because if the trigger is set to off, as you can see here, the waveform will continuously move, okay? So even if I press, I might see a waveform, you can see there, okay? Let me do that again. I press the waveform. Press it. There. Okay, so I will see the waveform and then it will go move. It will move again. So it will go off screen. So in order to capture at least one waveform, what I'll do is this, okay? I'm gonna press the push button switch on the circuit. Once I see the waveform, I'm gonna change the trigger setting to from off. I'm gonna set it to EXT, extended to EXT. So from off to EXT. Let's see if I could capture one waveform for with that procedure. Let me see. There, EXT. There. Let me try to get a clearer waveform. Okay, it's hopefully somewhere in the middle. I'll switch it off again. Okay, let me try to capture one waveform. Okay, EXT. There. Okay, this waveform I have. Okay. Now, okay. At this point, let me just make the display bigger so you can easily see that. Okay. Okay. Again, the black waveform is the output voltage. Is the output voltage waveform. You see here the LED is on when it's at this point, and it's going to turn off. Okay, after a few seconds, a certain period. Now, that period is determined by the blue line here. The blue line, as I mentioned earlier, is the waveform of the capacitor voltage. This is the capacitor voltage waveform. You can see here that the capacitor is charging. Okay? Then at this point, it will start to discharge. So while the capacitor is charging, you can see that the LED is on. And once it hits 2/3, based on our discussion earlier, 2/3 of the supply voltage, the capacitor will now suddenly discharge quickly. Now, let's verify this is 2/3. That point is 2/3. Just like in the previous video, I'm going to use one of my vertical cursors. Let me position that on the top peak or the peak of that capacitor voltage waveform and see the measurement here. Okay, you can see here. Okay, so I position the red on the top peak. Okay, see the Y1 and Y2 setting here. Both. It's at 3.31 volts. Okay, our supply voltage is 5 volts. And 2/3 of that is around 3.3 volts. So right on cue. Okay, just like what we have in the theoretical discussion. Okay, so when the capacitor voltage reached 2/3 of the supply voltage, it discharged, putting the monostable multivibrator circuit in its stable state. Okay. Now, the length of that on state, this one, the unstable state, or the on state of our LED while the LED is on, okay, that can also be measured. Okay. Now, to measure that, to take the measured value of that, I need now the horizontal cursors of my oscilloscope. Okay, you have here the one on the left is blue and the one on the right is the red one. Okay, so what I'm going to do, I'm going to position the horizontal cursor to the point where the capacitor voltage starts to rise. So I'm going to put it here. And I'm going to put the red cursor on the point where the capacitor started to discharge, okay, which is the point here. Now, here is the period of time when the LED is on, okay? You can actually compute for that, okay? Or you could actually take the measurement of that through the X setting here, just like in our previous video, X red and X blue, okay? So how do you compute for this one, okay? So this would be 1.3 seconds here, 1.3 minus 802 milliseconds. So this 802 milliseconds is also 0.8 seconds. So you got 1.3 seconds minus 0.8. So approximately around 0.5 seconds. Half of a second. Based on our measured value. Half of a second. Now, we can actually compute for that. Let's try to verify that measured value. Okay, by getting the theoretical computed value of that on state. Okay, that on state of our monostable multivibrator circuit. Okay, I have a calculator here. The formula I gave on the theoretical discussion earlier. Okay, based on the formula, okay, the formula is actually 1.1. Okay, let me turn on my calculator first. Okay, the formula is actually 1.1 multiplied by the value of the capacitor. Okay, let me start with the resistor first, okay? R1, the resistor R1, the one connected to 5 volts, okay? Which in our circuit, that's the 10,000 ohm resistor. So I have 10,000. 10 kilo ohms, right? Okay? Now, 10,000 ohm multiplied by the value of our capacitor. The capacitor we use here, the original one, is a 47 microfarad capacitor. So it will be 47 times 10 to the minus 6. There. Okay, let me press the equal sign. Okay. I'll press S to me so that you can see it. So, what I'm seeing there on my computed value, it says 0.517 seconds is the unit. Okay, so based on my computed value is 0.517. The length of that on state, the unstable state, should be 0.517 seconds, or around 500 milliseconds, 570 milliseconds. So based on my computed value is 0.517. Based on our measured value, is around 0.5, almost 0.5 seconds. So, see, it's fairly close. Computed value is fairly close to the measured value, which more or less confirms our theoretical discussion earlier. So with that, I bring to a close this video. And as always, I would like to encourage everybody to keep learning, keep experimenting, and I hope to see you next time here in Derricktronic.